Welcome back to the discussion on time-dependent perturbation theory. So, in the last session, what we have discussed is we have found a unitary transformation which will represent the dynamics of the state in interaction picture. Okay, so suppose psi of t represent the state of the system in the interaction picture. Then its time evolution can be represented by using an operator u, represented as ui t t0 psi at t0 interaction picture. Okay, so once you know this ui, then we could be able to find the evolution of state, and thereby we'll get the transition probability. It is how the perturbation leads to the new possible states. Okay, so that is what we have discussed in last lecture. Okay, so I will just revise what we have done. So we have an Hamiltonian h is equal to h0 plus vt. This V is called the interaction part and H0 is called the free part. It is completely time independent and V is time dependent, and V is switched on for a small amount of time. So this V of t is non-zero for a small time interval, 0 less than t less than tau. So for the duration tau, it is non-zero and it is 0 otherwise. Then what would happen is the system may undergo a transition. Okay, it will move from one state to the other state. Okay, due to this perturbation, and we also assume that this perturbation does not leads to any new degrees of freedom. Okay, so it is not invoking any new degrees of freedom. So therefore, the total Hilbert space, there will not be any change in the total Hilbert space of the system. The Hilbert space of the system will remain as the Hilbert space of H0. Okay, so there is no need to invoke the new states here. Okay, so we'll continue with our discussion. So discussion is how to find this UI. Okay, now to find this UI, so what you can do is in interaction picture, we know that the equation of motion in interaction picture is written as IH cross dou psi of ti dot t equals the interaction part of the Hamilton Vi of t psi of ti. So this we already proved it in during the derivation of discussion on interaction picture. Okay, so this psi of ti, so psi of t is the state of the system in interaction picture at the time t. So that can be written using this equation. So I can rewrite this equal to IH cross dot by dot t ui t t0 psi at t0 in interaction picture equals pit ui t t0 psi at t0. Okay, now here the derivative is with respect to t. So therefore the psi of t0 in interaction picture can be taken as a constant. Okay, so this equation becomes IH cross dou ui by dou t times psi of t0 I, then vi ui psi of t0 at I interaction picture. Okay, so basically what we can do is this psi of t0 I would cancel. They are present at both spaces. Okay, so hence I can write this equal to IH cross dou ui t t0 dot t equals vit ui acting on t t0. Okay, so the action of IH cross dou ui by dot t on psi of t0 I is same as the action of vi times ui on psi of t0 I. So that is why I can remove this psi of t0 I here and we'll get a new equation. Now we can make a small rearrangement and integrate this equation. Then what you would get is it would become IH cross UI T0 limit T0 to T, and on the right side we'll get integral from T0 to T VI T UI T T0 dt. Okay, so on the left side, if you put the limit IH cross, this become UI T comma T0 minus UI T0 comma T0 equals integral T0 to T VI T UI T T0 dt. Okay, now this UI T0 to T0. Okay, so this is basically the unitary transformation which connect the state in the interaction picture at T0 to T0. Then this should be equal to 1. Okay, is it okay? It is the psi of T0 I, psi of T0 I is connected through UI T0 T0. So since both these are same, this should be equal to 1. So hence I can write the form of UI T0, then that would be equal to 1, okay, 1 plus 1 by IH cross integral T0 to T VI T UI T comma T0 dt. Okay, now so this is the equation for UI. So you have to note that this is not a solution, because if you carefully look at this equation, we have UI on right side as well. So this is not a solution for UI. Only thing is it is an integral equation. Okay, so I think in order to avoid the confusion, what I can do is, so here dt is an integration variable and t is also put in the limit. So better I can put a prime over this integration variable. So instead of putting t as an integration variable, just puts t prime as the integration variable. Okay, so this is not a solution for this equation. So this is the integral equation of UI. Now again, one point you have to note that, so till now we have not made any kind of approximation. We have not done any kind of approximation till now. Next we are going to apply the approximation. Okay, so what we'll do, so better we can copy this integral equation of UI. Okay, so better I am going to change the variable slightly again here. Okay, so this UI, the integral equation of UI T comma T0, I can write 1 plus 1 by IH cross integral T0 to T VI. This is an integration variable, so I will just putting as T1 UI T1 T0 DT1. Okay, now how to get as a solution for it. Okay, so we have UI here. Okay, so UI equation I can write here now, but that UI is already present on the right side. So what you can do is I can give Now I can substitute the expression for ui t1 t0 from this equation here. Okay, so then what I can write is equal to 1 plus 1 by ih cross integral t0 to t vi t1. Now this ui t1 t0 will be replaced by this equation. That is, instead of u1, this ui t0, that I am going to denote by symbol ui t1 t0. So ui t1 t0 would be 1 plus 1 by h cross t0 to t1. Okay, and all others are same, and so there is a prime symbol here. So that is the integration variable. So this integration variable t prime I will change with t2. Okay, so then I can have this ui t1 t0 as 1 plus 1 by ih cross integral t0 to t1 vi at t2 ui t2 comma t0 dt2. Okay, so better we can expand it. Okay, and integration variables here would be other than integration variable dt1. Okay, which gpi is here. So this I can write as 1 plus 1 by ih cross. The first term would be integral t0 to t vi t1 dt1 plus 1 by ih cross square integral t0 to t vi t1, then integral t0 to t1 vi at t2 ui t2 comma t0 into dt2 dt1. Okay, now this the number of terms now increased. Okay, now we have a ui again here. So this is again not a solution. So what you can do is I can substitute this ui t2 t0 again from our first equation. Okay, so instead of t1, what I will do there, so instead of t1 I will use t2. Okay, so there is a t1 here, I'll put here t2. Okay, so then I can get some more terms in this expression. Okay, so better I will write it to get a better understanding. Okay, so in the next stage, so again ui t comma t0, first term is 1 plus 1 by ih cross integral t0 to t vi to t1 dt1 plus 1 by ih cross square integral t0 to t vi t1 integral t0 to t1 vi t2. Okay, now this ui I can write as 1 plus integral t0 to t2 vi t3 ui t3 comma t0 into dt3 times there is already dt2 dt2 dt1. Okay, so this curly bracket is this. So again, we can simplify it. 1 plus 1 by IH cross integral T0 to T VI dt T1 dt1 plus 1 by IH cross square integral T0 to T integral T0 to T1 VI T1 VI T2 dt2 dt1 plus 1 by IH cross all cube integral T0 to T1 integral T0 to T integral T0 to T1 integral T0 to T2 VI T1 VI T2 VI T3 UI T3 comma T0 D T3 D T2 D T1. Okay, so if you continue this procedure, we'll get infinite number of terms in this series. So basically this UITT0, okay, UITT0, I can expand in a series. So this series is called Dyson series. Okay, again recall, we have not made any approximation till now. Now we are going to make approximation in Dyson series. So since we got a Dyson series, what we can do is in the first order approximation, we can take only the first two terms. Okay, that is the linear, only the first integration in time. So in the first approximation, the solution for UI will contain only these two terms. Okay, so the term 1 is a trivial quantity, so I cannot take the 1 as an approximation, then it means there is no evolution. So in order to get a non-trivial solution for UI with the time, I have to take the first two terms as the first approximation. That is basically our original equation. If you go back, what we have got is the integral equation for UI is this. So this, if you put this UI t prime t0 is approximately 1. Okay, so if this UI t prime t0 is approximately 1, then what you will get UI t0 become 1 plus 1 by h cross t0 to t vi t prime dt prime. So that is basically called the first approximation. Okay, so we'll get the first approximation, the time dependent perturbation theory will get the first approximation for UI if you take the first two term. So I can write it as a first order approximation. Now what would be the second order approximation? The second order approximation we'll get if you take the first three terms. If you take the first three terms, we'll get the second order approximation. Okay, now here we have no third order approximation term here, because in order to get a third order approximation term, what I have to do is I have to approximate this UI T3 T0 approximately as 1. If you approximate this is 1, then we'll get the third order approximation. And if you want a fourth order approximation, what you have to do, you have to expand this UI T3 T0 in a series again, and we'll get the fourth order approximation and so on. So we can get the higher order approximation if you want. Okay, so So this is the approximation that we are going to use. So if you want the first order approximation, we will take the ui as only the first two term. Okay, so the first order approximation, so the first order approximation ui tt0 is written as 1 plus 1 plus 1 by ih cross integral t0 to t vi t1 dt1. Okay, and the second order approximation, the second order approximation, or this first order approximation, I can write ui in bracket 1, and second order approximation I can write ui, the second order t comma t0, that can be written as 1 plus 1 by ih cross integral t0 to t vi at t1. So t1 is the integration variable plus the second term 1 by ih cross square integral t0 to t vi t1 integral t0 to t1 vi at t2 dt2 dt1. So that is the second order approximation term. And what would be the third order approximation term? Can you guess? Okay, obviously you can guess it. That is, apart from these three terms, there will be the next term, 1 by ih cross whole cube integral t0 to t vi t1 integral t0 to t1 vi t2 integral t0 to t3 vi t3, then integration t3 t2 t1. Okay, if you want that bracket, we can put it. Okay, now we can go back to our main problem. So our main problem is we have to know what is the transition probability due to the perturbation. Okay, so what kind of transition would be possible with the perturbation? So our next question is transition probability. So that is the state of the system at t0 will move to a new state at a time t. Okay, so this can be some state n, this can be some state m. So what is the probability for this transition? So how to find that? So the probability of the transition, so some from initial state psi I and some final state psi f, the transition probability we can find from the inner product psi f at t u I t t0, then psi I at t0. If you take the mod square of this, we'll get the total transition probability. Okay, so in the next class, we'll focus on this topic, that is how to find the transition probability using time dependent perturbation theory. Okay, so we'll just summarize what we have discussed till now. So remember, we have started with the Hamiltonian of the form h0 plus v of t, where v of t is present for a small amount of time, and our the main aim of this topic is to find the transition probability of the system. It is if you give some kind of perturbation to the system, then what is the probability to achieve a new state? For example, if the system is a two-level atom. If you give a perturbation, so what is the probability for the excitation? That is what is the probability to go to the ground state, or what is the probability to go to the excited state. So that kind of probability we have to calculate. And for that, finally, we have to know the form of ui, because ui gives the time evolution. It mathematically gives the time evolution of the system in interaction picture. But getting the expression for ui is not very straightforward, because ui obeys an integral equation. Okay, so we have to solve that an integral equation to get the solution for ui. And solution for the integral equation is again not very straightforward. What we'll do is we'll find a series solution, okay, a series expression for ui. Okay, and there we'll use certain approximation. So if you are going for first order approximation, I will put ui t1 t0 as 1. So that is basically called the first order approximation. Then the equation become 1 plus 1 by h cos negative t0 t pi t1 dt1. If you are going for second order approximation, I will put this approximately equal to 1. And when you're going for third order approximation, okay, so when you're going for third order approximation, what I'll do, I have to do this ui t3 t0 approximately 1. Okay, so this complete series is called Dyson series, and we'll get the expression for ui at the different orders of approximation. And from that, we can calculate the transition probability. So if you want the nth order uh, result, I have to put UIN, the expression for UIN. So this can be calculated because we already know the expression for VI. The time dependence of VI is known to us. So there is no much problem for us. So this VI is known. So I can do that integration. There is no difficulty for it. And we can find the transition probability. So in the next class, we'll discuss how to find the transition probability using this time dependent perturbation theory. So thank you.